Functions have many properties that we want to study and understand. Some of the properties will be explored here, where we talk about things like the vertical and horizontal intercept and where functions are going to be increasing and decreasing. The intercepts of a function often have real-world meaning if our function is modeling something relevant to the real world. So being able to identify where these things happen is often helpful for us to figure out information regarding what we're doing. However, we can also do this algebraically for functions that don't have real-world applications to see where they cross through our axes. The vertical intercept of a function is the point where the function crosses through the vertical or dependent axis. This happens when x equals 0. In general, what this is going to look like is going to be where we cross through the vertical axis. So here is an example. Another example, maybe something that's more linear in nature. Or we could have something that's much more curved. But the spot where we cross through that vertical axis, we call the vertical intercept. It's also referred to as the y-intercept, as y is a typical dependent value, which represents our vertical axis. In order to find this value, we consider where x equals 0, because when x equals 0, the corresponding y value, or dependent value, is exactly where we cross through the axis. Now, for a vertical intercept, you could have one vertical intercept, or if you have a restricted domain, you could have 0 vertical intercepts. The horizontal intercept is going to be where our function crosses through the horizontal or independent axis. This is going to happen when the dependent value equals 0. So for example, if we have a function that looks like this, our horizontal intercept is over here to the left. It's where we cross through the horizontal axis. Now, as you can imagine, we could have many horizontal intercepts like this. You can see here, we have a whole lot. Or we could have one, like we saw in the first example, or we could have none. We could have a function like this that doesn't cross through the horizontal axis at all. So for horizontal intercepts, sometimes we have 0, sometimes we have 1, and sometimes we have multiple. It really depends on the function. But in order to solve for this, we're considering when y equals 0, because when y equals 0, that's when we're on the axis. So if we have a function, we can set y equal to 0 to find these intercepts. So let's go ahead and practice this with some of our different types of functions. So let's start with a function x squared minus 2x minus 3. When we have a formula, we can use the algebraic rules to help us find these intercepts. So remember, if we're looking for the vertical intercept, which I'm going to write down as vi, that happens when x equals 0. So if we take x equals 0 and we plug it into our function, let's see what we get. We have 0 squared minus 2 times 0 minus 3. So what we're going to do here is we are going to consider what the value of y is, and that will be our vertical intercept. That gives us a value of -3. So our vertical intercept here is the point 0, -3. Now we can look for our horizontal intercept. Remember, our horizontal intercept, which I'll write as hi, is going to happen when y equals 0. So if we take y and set it equal to 0, we have 0 equals x squared minus 2x minus 3. So here we have a quadratic function, which means you're probably going to want to factor this to find the roots. When you factor a quadratic equation, you are looking for two numbers that multiply to give you the last term, but add up to give you the middle term. So here, I'm going to get x minus 3 and x plus 1. If you're more comfortable using the quadratic equation, that's fine too. So that tells me that I have two places where my function is going to intersect my horizontal axis at x equals 3 and x equals -1. So here I have two horizontal intercepts. So those points are going to be 3, 0 and -1, 0. And if you remember from earlier, we did graph this, and this function looked like this. So that makes sense to what we've said here about our intercepts. Our vertical intercept happened at -3, which is below the x-axis. That's what happened here. And our horizontal intercepts were at 3 and -1, which matches up with what the picture of this function looks like. If we want to do this based on a graph, we would take the picture of our graph and we'd look for the places where our intercepts happen. So again, we'll start with the vertical intercept. The vertical intercept is what happens when x equals 0. So we're looking on the vertical line and we see that it intersects at 0, 0. Again, a vertical intercept can happen one time or no times, but here it happens once. Our horizontal intercepts, however, can happen at many places, as you can see happens here. So let's go ahead and go from left to right and see if we can identify all of our horizontal intercepts. The first one I see is right here. That looks like it happens at roughly -6.5 and y equals 0. That's our first one. Our next horizontal intercept is a little bit past -3. So let's call that -3.2, 0. Our next one happens at 0, 0. That's really interesting because that was also our vertical intercept. Sometimes our vertical intercept is the same as our horizontal intercept. And that happens when you have the value 0, 0, because that happens when both x and y equals 0, which is how we were finding our intercepts by setting one of those values equal to 0. Our next intercept happens a little bit past 3. So here, we'll call that approximately 3.2, 0. And then finally, our last point here is going to be approximately 6.5, 0. I want to note here that I'm approximating where this point happens. So if you saw that picture and thought, hey, that looks more like 3.1, not 3.2, that's probably fine, as long as you're in the general ballpark. We're approximating here, so as long as we're pretty close, then we're okay. But it's definitely past 3 and not very close to 4. So something like 3.1, 3.2, or even 3.15 would be okay here. So here you can see we have one vertical intercept and we have 1, 2, 3, 4, 5 horizontal intercepts. And we can read those right off of the graph. Our next case here, we're going to look at a table. So now, because we have a qualification on intercepts based on what the x and y values are, we're going to use that to help us determine where the intercepts are on the table. So remember, for a vertical intercept, we said that that's going to happen when x equals 0. So here, if we consider where x equals 0, that happens in the very first slot of our table, x equals 0. When that happens, y equals 30, which means our vertical intercept is going to happen at 0, 30. Our horizontal intercept, if we have one, is going to happen when y equals 0. So here, what we need to do is we need to go to our dependent values, which here are f of x, and see if there's any places where y equals 0. Remember, this could happen 0 times, 1 time, or many times. So we have to consider all the values of f of x because there might be multiple instances where it equals 0. What we see here is that it only happens once. It happens right over here at the end of the table. It happens when x equals 6. So here I have one horizontal intercept when y equals 0 and x equals 6. So my horizontal intercept is at 6, 0. Remember, coordinate points are written x, y, so we write the x value first. So on this table, we had both a vertical and horizontal intercept. Finally, we want to consider what happens when we have a word problem. So here, remember that the cost of ice cream in Mathtown was a function of the number of toppings t to be put on the ice cream. So c was a function of t. And we said if the shop offers 10 different toppings and the cost of an ice cream is given by c equals 5 plus 0.25t, Identify the horizontal and vertical intercepts of this model and determine if they have relevant meaning. That last part's important because now we do have a function that models what's happening. And the function itself may have intercepts that don't make sense in this case. So we can solve for them, but then we need to make sure that they actually make sense. So let's start with the vertical intercept. Remember, the vertical intercept was when x equals 0. We don't have an x here. So we have to remember, it wasn't when x equals 0, it's when the independent variable equals 0. So if we change the independent variable from x to t, that means we're considering what happens when t equals 0. So here, when t equals 0, c is going to equal 5. Because if I go to my function and I plug in t equals 0, I get 5 plus 0.25 times 0, which gives me 5. Remember, cost is in dollars, so that's $5. So now we have to see if that makes sense. Toppings equals 0, cost equals $5. That makes sense here because that means that if you get no toppings on your ice cream, it's still going to cost you $5 to buy that ice cream. So that makes perfect sense in this context. Now let's consider horizontal intercepts. So again, for a horizontal intercept, we want to consider when y equals 0. But again, it's not really when y equals 0, it's when the dependent variable equals 0. So here my dependent variable is c. So if c equals 0, then I'm dealing with the fact that 0 equals 5 plus 0.25 t. So if I were to solve for t here, I would subtract 5 from both sides, and I would get negative 5 equals 0.25 t. T is going to equal negative 5 divided by 0.25. And when you crunch that number in your calculator, you're going to get t equals negative 20. So what that says to me in terms of this context is if I order negative 20 toppings, then the cost will be $0. Well, that doesn't really make sense. You can't walk into a store and order negative 20 toppings. So even though this function has a horizontal intercept in terms of the function by itself, because of the context of what's happening here, we would say that there are no horizontal intercepts. Because here, there's an unwritten rule about the domain here. The domain, given the context, is that t has to be greater than 0, The domain here is that t has to be greater than or equal to 0. Therefore, it doesn't make sense for us to have a spot where c equals 0, because in that case, t is going to be negative. So our popcorn vendor at Fenway sells popcorn for $6 a bag. Let R be the revenue in dollars for one night sales, and P represents the number of bags of popcorn sold. Her revenue at any time in the evening can be modeled by R equals 6P. Identify the horizontal and vertical intercepts of this model and determine if they have relevant meaning. So again, the vertical intercept is going to be when our independent variable equals 0. Here, my independent variable is P, which represents the number of popcorn bags. So if I let P equal 0, then R will also be equal to 0 because 6 times 0 is 0. What that means is if I sell 0 popcorn bags, that my revenue will be $0. And that makes perfect sense in this context. So my vertical intercept, 0, 0, makes a lot of sense. Turns out my horizontal intercept is going to be the same thing, because if R equals 0, that tells me that P equals 0. And again, what that means is if I didn't make any money in revenue, I didn't sell any popcorn bags. So that's the same statement, just spinned a different way. So my vertical and horizontal intercept here are the same, and it makes sense in this context. So that means that they exist and we can attribute meaning to them. So these intercepts often have important meaning for us. So being able to see them or identify them from our functions is going to be an important part of the things we do later on. The next step in describing our functions is going to be to talk about when our functions are said to be increasing and when they're said to be decreasing. This is going to become the underlying premise of a lot of analysis that we do later graphically in this calculus course. So this is a first step to laying the foundation for our graphical analysis. So in calculus and in mathematics, a function is said to be increasing if the values of the dependent variable increase as the values of the independent variable increase. So what does that mean? One of the key things here is that we're talking about what happens as the independent variable increases. So for the sake of discussion, let's consider the independent variable to be x. So we're talking about what happens as the x values go up. As the x values go up, the y values go up. That's what it means to be increasing. Consider a graph. Think about what you think an increasing function would look like. Got it? Okay, well now I'm going to draw one. Here, we read a graph from left to right. So if we're talking about what happens as the x values go up, we're talking about what happens as we look from left to right. And as we look from left to right, we can see that the y values are going up. So therefore, that function is said to be increasing. There's a lot of different ways that functions can increase. They can look like I just drew on the first picture, which is pretty linear. They can be curved in many ways, but as long as they're going up from left to right, then that picture indicates that they're increasing, because as the x values go up, the y values go up. Similarly, a function is said to be decreasing if the values of the dependent variable decrease as the values of the independent variable increase. I want you to notice that this last line is the same as before, because what we're always doing when we're evaluating what's happening is determining what's happening as the x values increase. So for all tests that we do, whether they're on a table or a function or a picture, we ask what happens as x goes from left to right or from small to big as they get bigger. What happens to that y value? If the y values go up, we're increasing. But if they go down, that means that we're decreasing. So here, let's again look at a picture. So again, we're asking what happens as we move from left to right. And you can see that those y values are going down. So that is a decreasing function. And again, it doesn't have to be linear. There's lots of ways a function can decrease. But the key here is that as the x values get bigger, the y values get smaller. They're going down from left to right. So that's what it means to be a decreasing function. So one of the important things that comes with this is what happens when you change from increasing to decreasing. So as a side note, if you have a function that does both increasing and decreasing, so for example, something that looks like this, at this point, the point where we change from increasing to decreasing, we consider that point to be constant. So at that particular moment, when you've reached the point where you're going to change from either increasing to decreasing or decreasing to increasing, that one point is constant because it doesn't do either at that moment. That's the point where we're changing. So that's the word we use here. So let's look at some examples of increasing and decreasing and see if we can figure out how to do this on our different functions. So let's start with our formula, x squared minus 2x minus 3. So if you remember from earlier, we tested a whole bunch of points in this function to see what it was doing. That's also a good idea for a case like this, to get a general sense of what's happening. But even better would be to graph this function. So again, when you're graphing a function, you can plug in some points, check, see what's happening to get a general sense of what's going on. You can also use a graphing calculator when you're doing your homework to figure out what this function may look like. So here, if we plug in a few points, we know that f of 0, which means we're going to plug in a 0 everywhere we see an x, is going to give us -3. F of 1, if we plug in a 1 everywhere that we see an x, we're going to get -4. If we plug in a 2 everywhere we see an x, we're going to get -3 again. If we plug in some negative numbers here, if we plug in a -1, we're going to get -1 squared, which is 1, plus 2 is 3, minus 3 is 0. And if we plug in a 3 here, 3 squared is 9. 9 minus 6 is 3. 3 minus 3 is 0. So we have a function, and squared functions take on a shape that's called parabolic. Okay, so it's going to look like a U or an upside down U. It's a parabola. And we know that it's going to cross through at -1, x equals -1, and x equals 3. Those are intercepts. So at -1 and at 3, we have our intercepts. And then here, we also have a vertical intercept at -3. So when x equals 0, we're going to cross through at -3. So we'll label that. But we can also see that we go down further than -3. We actually come down to -4, which is right around here. So it doesn't have to be perfect, but it's a basic U shape here. And we know that this continues going up on both sides forever and ever. And then here at the point 1, -4, we end up finding the minimum of our graph. Now, this is important because in order to determine where we're increasing and decreasing, we need to figure out where we turned around. So here, if you look at this picture, again, when you read a graph or when you consider increasing or decreasing, you're considering what happens as the x values move from left to right. This function had a domain of all real numbers, which means that we're starting on the left-hand point of -infinity. So from -infinity all the way until x equals 1, our function is decreasing because it's moving in the downward direction from left to right. Don't let the arrow on the end confuse you. That just means that the graph continues up. We read the graph from left to right. So we're moving from left to right, and we're looking at what our function's doing. The y values are coming down. So that means that we are decreasing. So we are decreasing. So we are decreasing from -infinity all the way until x equals 1. When we talk about where things are happening on a graph, when we're describing things, and we're talking about intervals where things are happening, we describe them in terms of their x values. The x values help us locate where on the graph we're talking about things. So when we talk about increasing or decreasing, we're going to talk about where the independent variable is when those things are happening. So here, that's from -infinity all the way until x equals 1. But then at 1, our graph turns around. And as we move from left to right away from 1, you can see that the y values are going up. So that means that from 1 all the way to infinity is where my function is increasing. So I'm going to be decreasing from -infinity until 1 in terms of the x values, and then increasing from 1 to infinity. I want you to notice that I use strictly less than and greater than signs and not equal to. Remember, we talked about how we use strict inequality signs with our infinities. We never use the equal to with infinities. And at 1, at that point, we're constant, which means that at 1, we're not increasing or decreasing, so we don't include it in either of our intervals. So now, let's go ahead and take a look at this on a table. So if we want to look at where a table is increasing or decreasing, again, we're considering what happens as x gets bigger. The way that tables are set up are increasing values of x. So it's already set up for us to analyze where it's increasing or decreasing because the x values are lined up sequentially getting bigger. So what we need to do is we need to consider what the y values are doing. So my first y value is 37, then 27, then 19, then 3. So those values are continually going down. They don't stop and turn around and come back up. They could. We could have parts that were increasing and decreasing. But in this case, these numbers continue to go down. So this function for this table is decreasing everywhere. And we can write that. We can say decreasing everywhere. Okay, so when you have a table, you need to look at the dependent values and see whether they're going up or going down. And that will tell you where that table of data is increasing or decreasing. When we have a graph, we're going to look at the intervals to determine where they're going up and where they're going down. So here, I can separate out the spots where things are turning around, and that will help me define my intervals. So again, I'm going to go from left to right. So the first interval here is going to go from -2 to about -1.1. So from -2 to -1.1, my function is decreasing because that function's moving downward in terms of the y values as I move from left to right. Okay. My next interval, which is going to be -1.1 up to 0, that interval is increasing because it's going in the upward direction as I move from left to right. My next interval, 0 to 1.1, is again decreasing because I'm moving downward from left to right. And then 1.1 to 2, I'm again increasing because I'm moving upward from left to right. So again, I could have used my inequality notation, but I can also use my open parentheses, my open interval notation to note the same thing. So here again, I'm going to use open parentheses because at the point where I turn around, I do not include that point. So here, I can see the intervals where I'm increasing and decreasing and read them right off the graph. Finally, I want to look at some word problems and determine if I can figure out where they are increasing or decreasing. So let's start with the ice cream shop. Remember, the cost of our ice cream is given by C equals 5 plus 0.25t. And so here, my t values are going to vary from 0 to 10. So if I plug in 0, I get C equals 5. If I plug in 1, I get C equals 5.25. Remember, we did this with domain and range. So then, if I plug in t equals 3, I'm going to get 5.75, so on and so forth. I can see by the setup of this problem that as I plug in various values of t, my c values are going up and up and up. So this function is increasing. Since there's no places where I stop increasing or where I start decreasing, I can just say in general that the function is increasing. Similarly, if I come down to my popcorn example, my function was that R equals 6 times P. Remember, R is revenue, the amount of money I take in, and P is the number of popcorn bags that my vendor sells. So here, P can take on integer values starting at 0 and going up to who knows how high, however many bags of popcorn she can hold in a night. So 0, 1, 2, 3, as I plug in those numbers, my R's continue to go up by a factor of 6. So when P equals 0, R equals 0. When P equals 1, R equals 6. If I were to graph this, I would see it's a linear increasing function that has a slope of 6. So here, again, in this scenario, my function is an increasing function. So when I'm determining whether functions are increasing or decreasing, I'm always considering what happens as my independent variable increases. What happens to the dependent variable?